Bismillahirrahmanirrahim. Dear students, grade 12, and the lecture number is 67, and chapter number is 24, last chapter, and we started already spectrophotometer. Spectrophotometer, modern methods of analysis. Modern methods of analysis. So in the previous lecture, I told you about the spectroscopy, spectrophotometer. So there are different regions in spectroscopy. So first we are going to start infrared spectroscopy. The instrument used to measure the amount of electromagnetic radiation absorbed by the compound is called a spectrophotometer or only spectrometer. The instrument used to measure the amount of electromagnetic radiations absorbed by the compound is called a spectrophotometer or only spectrometer. It consists of light source of radiation with a prism that can select the desired wavelengths. IR, visible, ultraviolet, which are passed through a sample of the compound being investigated. The radiation that is absorbed by the sample is detected and recorded on the chart against the wavelength and wave number. Wavelength, you can use wavelength, you can use wave number also. Absorption peaks are plotted as minima in infrared and usually as a maxima in the ultraviolet spectroscopy. So this is the spectrophotometer, and then we use the infrared IR region. Infrared region, which is above the visible. Infrared region extends 2.5 to 16 micrometers. 2.5 to 16 micrometers or 4,000 to 625 per centimeters. So this is the infrared radiations. Although this radiations are weak, it does supply sufficient energy for bonds in a molecule to vibrate. In the previous example I told you, in the infrared bonds vibrate. By the vibration of bond we can analyze it. Vibration of bonds. The molecular motion that is affected by the absorption of quanta in the infrared radiation is the vibration motion. Already I told you, vibration. The studies of vibration spectra of molecule lead to the information on the flexibility of the molecules. The small displacement of the constituent atoms from their equilibrium position can be seen in terms of vibrational motion of the atoms. Such changes in the bond length produce a change in dipole moment of the heteronuclear molecules. Hetero means different, HCl, hydrogen iodide, hydrogen bromide. Heteronuclear atoms and oscillating dipole couples with the electric field of radiation and exchange of energy takes place. We have the example of spectrum of propanone. Propanone. This is the propanone, or we call acetone. Propanone or acetone. So dear students, if you see the infrared spectrum of the propanone, actually propanone has two. One is a alkyl group, carbon hydrogen bond, and other is a carbon oxygen. Two. Carbon hydrogen bond and carbon oxygen bond. So when you are going to plot a spectrum by the wave number per centimeter, wave number on the x-axis, and transmittance percentage of absorptions, percentage on the y-axis. So you will see the peaks, different spectrum. Page number 346. Open page number 346. So you will see the peaks. So dear students, already I told you this spectrum you can see is quite complicated. Complicated it is. Many peaks you are seeing. But propanone is a very simple compound, two alkyl groups, hydrogen and carbon, and in between there the carbonyl group is there. There with a simple one, there are three kinds of bonds you can see here between the carbon bond, carbon hydrogen bond, carbon oxygen bond. Three kinds of bonds you are seeing here. The complexity arises because each bonds can vibrate in a number of different ways. In different ways, carbon-carbon bonds vibrate different. Carbon-hydrogen bond, carbon-oxygen bond. So they have vibration in different pattern, different ways. And the vibration can interact with each other. Nevertheless, it is possible to see some characteristic peaks. These are called peaks. Characteristic peak we can differentiate of absorption, which can be used to identify the functional group in the molecule. So by using these peaks we can identify the functional group of the molecule. So you can see in the spectrogram or spectrum of the acetone, which is shown in 24.3 figure, that x-axis is there the wave number, y-axis is there the transmittance in the percentage. So there are some characteristics, absorption of some common bonds. In the spectrum of propanone above figure, strong peaks about 1720. 1720 per centimeters. Strong peak. 1720 strong peak. You will see the downward big peak, strong peak there is, which is exactly at 1720, and this shows carbonyl functional group. This shows carbonyl functional group at 1720 absorbance. This is in the wave number. But if you write in the wavelength, it will be inverse. These peaks will be up because wave number is inversely proportional to wavelength. So this is the wave number per centimeter. But if you use centimeters, then it will be go up. These peaks will be going up the upper side. So this is a strong peak at about 1720, which shows the carbonyl functional group. The weaker absorption at 300,000 centimeters. 3000. If you see the spectra, you will find 3000, which is the carbon and hydrogen bond. Carbon hydrogen bond. At 3000 per centimeter wavelength, you will see the carbon hydrogen bond. This peak is a weaker even though there is a more hydrogen atoms in the molecule. So in the spectroscopy, the strength of the peak is of characteristics of bond itself, not the number of bonds present. Characteristics: carbon hydrogen bond, carbon oxygen bond, carbon carbon bond. Don't see the numbers. So we have these known in books, then we have to match with the actual spectra drawn by the student. You can see this carbon and hydrogen in the table. Carbon and hydrogen bond, alkanes, alkenes, arenes, 2840 to 3095. Intensity: N for medium, S for strong, both medium and strong. Medium and strong. Carbon hydrogen in the alkanes, alkenes, arenes, medium and strong. And you have also aldehydes and ketones. Acid esters, carbonyl group is 1680 to 1750. This is a very strong. It is strong. This is somehow strong and also medium. So you can see these both lie in the same range. Carbon hydrogen 2840 to 3095. This is 3000. And for the carbonyl group in the aldehyde, in the ketone, in the carboxylic acid, 1680 to 1750. So this is 1720 in between. So this is a very strong peak. So by using this table, we will be able to draw the spectra of the any compound. This is a very sensitive and very interesting practice. When we are going to do in the laboratory by using different instruments to analyze different components, organic compounds and inorganic also, by identification of functional groups and other bonds, and by using different techniques. Already I told you, if you see the figure number 24.2, analysis of water in different ways, we are using here infrared spectroscopy. So by using infrared spectroscopy, we have to draw this spectra to analyze the compound. So this acetone has two bonds, carbon hydrogen bond and carbon oxygen bond. By using this, you can calculate and match with the original results. Now this is about infrared. Now there is also visible and ultraviolet spectroscopy. Visible and ultraviolet spectroscopy. Spectrophotometer. So visible and ultraviolet spectroscopy. Visible means the spectrum which we can see by the naked eyes. You done in the grade 11. Visible has two types. One is called continuous, another is called line spectrum. Invisible below this range. Visible spectroscopy, the wavelength is starting from the 350 to 750 or 400 to 750 nanometers. and ultraviolet is below 150 to 350 nanometers. So in the ultraviolet visible spectroscopy, absorption of ultraviolet 200 to 400 means 200 to 400. To 400, these are the peaks in the nanometers, and 400 to 700. Nanometers. So this can be seen, this cannot be seen. Red Gaia, all the colors violet to red. So radiation of molecules is associated with the extraction of loosely bond help each other, such as unshared electron. There are two types. Here. Just like these are the shared. One electron pair share the electron shared. These electrons are unshared. These are the unshared electron pairs we call lone pairs. Lone pairs, bond pairs. These are the bond pairs, these are the lone pairs. So here so this is the sigma bond and this is the pi bond. This is a sigma bond, this is a sigma bond. These unshared electron pairs. Sigma bond, pi bond. Single bond is called a sigma bond, and double bond, one sigma bond and one pi bond. Triple bond, one sigma bond, two pi bonds. Such as unshared electron pairs and pi bonds. From the lower energy occupied molecular orbitals, you done the grade 11 by trying the MO theory, molecular orbital theory. When the atomic orbitals are going to be intermixed or overlap to give two kinds of the molecular orbitals. One is called bonding molecular orbital and another is called anti-bonding molecular orbitals. Bonding molecular orbitals have a lower energy and anti-bonding molecular orbitals have a higher energy. That's why bonding molecular orbitals they have a lower energy, and the anti-bonding molecular orbitals they have the higher energy. Bonding molecular orbital sigma bond and anti-bonding molecular sigma star bond. So there are three kinds of electrons in sigma bond, in pi bond, and unshared electron pairs. Sigma bond, pi bond, unshared electron pairs. So which are denoted, these I told you this one. On the absorbed energy, any of these electrons can enter in the excited state, which are either anti-bonding star, sigma star, pi star. All molecules have a sigma and sigma star orbitals, but only those of pi orbitals have a pi star orbitals. Only the non-bonding electrons, and for non-bonding electrons to the pi star, pi to pi star, non-bonding to sigma star. So this is the here relative energy change diagram. This is the energy. Sigma bond is very strong, has the lowest energy. Sigma bond has the lowest energy. Then pi bond, then non-bonding electrons, then pi star, and last sigma stars. Sigma star has highest energy. Sigma star has the highest energy. So first he said that to sigma star. Sigma to sigma star. Then sigma, there is also pi to pi star. This is a pi bond. Pi to pi star. Then non-bonding to sigma star. Non-bonding to sigma star. This is non-bonding. Non-bonding electrons to sigma star, and then non-bonding to pi star. This is the relative energy involved in various electronic transitions. Now, dear students, here on absorbing energy of any of these electrons can enter excited. We jump from lower to higher energy. Excited state, which are either anti-bonding sigma star or anti-bonding pi star. All molecules have sigma and sigma star, but only those with the pi orbitals have pi star orbitals. So only the N, this is the N, this is the N to pi star, pi to pi star, and more rarely number N to sigma star. Excitations occur in the near ultraviolet radiations, near ultraviolet radiations, and visible regions, which are available regions for ordinary spectrophotometers. The energy required sigma to sigma star is very high, and therefore occurs in the vacuum ultraviolet below. This is the vacuum. This very high. Vacuum ultraviolet, this is the less than 200 nanometers, which is not usually accessible in most of the ultraviolet and visible spectrophotometers. The relative energy for the 3 electron transition detectable by the ultraviolet spectrometer is order of increasing n to pi star, these are accessible, n to pi star, and then pi to pi star, this is the pi to pi star, then n to sigma star, n to sigma star also. In fact, absorptions of ultraviolet visible radiation by a molecule result in the electronic transition from highest occupied molecular orbitals to the lowest occupied molecular orbitals. So dear students, this is about the visible and ultraviolet spectroscopy and how there is absorptions of the energy from lower energy level to higher energy level when they are going to be travel. So what happens and how the ultraviolet radiation is going to be formed. Quick quizzes. Then you have to solve this one. Then there is another very important nuclear magnetic resonance. NMR, nuclear magnetic resonance. Nuclear magnetic resonance NMR. So nuclear magnetic resonance NMR, as a name implies, is concerned with the magnetic properties, nuclear magnetic resonance, magnetic properties of certain atomic nuclei. Magnetic properties of certain atomic nuclei, that's why name is nuclear magnetic. All nuclei carry of charge and some of them also spin about their axis in a manner that is analogous of that in which electrons spin about their axis. The nuclei whose spin quantum number is 0, spin quantum number S, spin quantum number is 0. If the spin quantum number is 0, then what happens? Do not spin. They do not spin. The symbol L is used to denote the spin quantum number of the nucleus. The symbol L is used to denote the spin quantum number of the nucleus. Now, nuclear magnet. Nuclear magnet. A spinning charge, whether positive or negative, consisting of circular current, which generates a magnetic dipole along the spin axis. A spinning charge may be positive, may be negative, consisting of a circular current which generates a magnetic dipole along the spin axis. Since all nuclei carry a charge, spinning nucleus behave as a tiny ball magnetic. They have tiny ball magnetic. We call them nuclear magnet. All nuclei carry a charge. A spinning nucleus behave like a tiny ball magnet. That's why we call them nuclear magnet. Placed along spin axis and has a characteristic magnetic movement we call mu. Magnetic movement. Which we call mu or nu. Is in the absence of external magnetic field, the nuclear magnet are oriented in a random fashion. However, if they are placed under the influence of uniform external magnetic field, they can take up different orientations with respect to the applied magnetic field. In a quantized system, according to the quantum mechanics, the number of possible orientation of nuclear magnetic in an applied magnetic field is determined by the spin quantum number of the nucleus, which is given by 2L plus 1. 2L plus 1. You did in the grade 11 quantum numbers. Values of M are 0, 1, 2 and 3. This is the azimuthal quantum number. Small l is the azimuthal quantum number. It is not negative, started from 0. So when it's 0, it's the S. This is the P, this is the D and this is the F. SPDF. So this will give the number of degenerated orbitals. If I am going to apply when L is equal to 0, when L is equal to 0, 2 multiplied by 0 is 1. So S has only 1, it is not going to be root. It has no other degenerated orbital. S has no other degenerated orbital. So if you have the L is equal to 1, 2 multiplied 1 plus 3, so P has Px, Py and Pz, degenerated orbitals. Different directions but same energy. Different spins but same energy. So they have a Px, Py and Pz. And if you have a 2 multiplied by 2, 4 plus 5, D has a 5, dxy, dyz, dx square minus y square, dy, like this, there are 5. And if there are 3, 2, 3, 6 and 7, so that's why F has a 7 orientations. So that this is in the grade 11 you done in the quantum numbers, spin quantum number, principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number. These first 3 quantum numbers are explained by the Schrödinger wave equation, and the spin quantum number explains the self-rotation of electron. You know it has 50% plus half and minus half. Clockwise 50% rotation and 50% anti-clockwise rotation. So this is the same you done before. The absorption of the electromagnetic radiation by the nucleus to induce spin flapping. Induced spin flapping will take place when the frequency of the electromagnetic radiation is exactly equal to the precessional frequency of the nucleus. So the two frequencies are in the resonance, hence the term we call nuclear magnetic resonance. Nuclear magnetic, already I told you, is spinning charge, whether positive or negative, consisting in a circular current which generates a magnetic dipole along the spin axis. That's why we call nuclear magnet. And then the electromagnetic radiation is exactly equal to precessional frequency of the nucleus. These two frequencies are in the resonance. That's why we use term nuclear magnetic resonance, NMR. So dear students, we are going to finish here. Then we start the instrumentation. We are going to now start instrumentation. So we complete this whole topic which is given here for the spectroscopy. So thank you very much. We complete here.